Hi, everybody. Let's start with the prayer. Father, Son, Holy Spirit. Hail Mary. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners now and at the hour of death. Amen. All right, where is everybody? Emily, you're in the wrong seat then. That's fine.
Sorry, I should have said this.
Yeah, in the future, if you can just wait till after, like, we manage to make it through attendance. But that's not a big deal. Is Alex there? I can't see.
No, she's not.
Okay. All right. Is Kaylee back there? I don't know. Everybody's skipping today because I made it too clear there's going to be a homework quiz, apparently. I'm going to have to stop telling you guys when these are coming. Well, if we can't manage to make it to, if I have 7 people absent on a regular basis, it's kind of a problem.
Maybe you should just make a survey.
Well, like, look, you guys are doing the right thing. It's your slacker classmates that are finding reasons not to be at school when there's assessments going on, which is the problem. What's that? Well, you can let them know, all your friends, that, like, hey, stop skipping the homework quiz days when you know it's coming because Mr. Kulik's going to stop telling us. So, like, make sure to let everybody know, like, hey, stop skipping if you can be here, because this is like the second time we've done one of these, and it's like half of the class is gone, which is kind of a joke, right? What's the point of telling everybody if it's going to take it a week later anyways? So, yeah, Mr. Gluck's a little salty about it. Because we complain when we don't when we don't hear about it, and then you skip school when you know it's coming. Well, it's like, why should I bother telling you then? Not that they're all skipping school. I'm sure they have legitimate reasons to be gone. But quizzitis sounds like a likely symptom of at least one of us. So, anyways, last time we talked about section 8.4, and I asked you guys to work on problems 51 through 76. Let's start there with a couple of questions, or from previous homework is fine also. Alyssa?
Can you do 67?
Sure. So 67, we're asked to take our vector line equation and rewrite it into a slope-intercept equation. And the complication here on 67 is that instead of the equation being written in that standard IB component form, we're written in this linear combination form. So that's not a big deal. We just have a little bit of algebra to do to kind of sort things out. So what I'm going to do is I'm going to distribute the I and J's through. And then I'm just going to group the I parts together. Or I'm sorry, the parts without the T together. And the parts with the T together. Oops. Okay with that, Alyssa? So this then becomes just back into the IB component form. And then it's easy, right?
Yeah.
You know what to do from here?
Yep.
Okay. So just had to do a little rearranging, and then we're good to go. Who else? Luke?
Could you do number 47?
47?
Yeah.
Sure. So this says that a crate of negligible weight is being pulled up a ramp at an angle of elevation of 38 degrees with a force of 120 pounds. So that's describing some pull vector, so I'm just going to write down the relevant information, not the entire problem. You cool with that?
Yeah.
Okay. It says the ramp has an angle of elevation of 25 degrees. And since we're not given any indication of how long the ramp is, we'll just assume that's a unit vector and make the magnitude 1. And we're asked what is the amount of force being directed up the ramp. So since this is a unit vector problem, I know I can use the shortcut to do this and just do the projection of that pull vector onto the ramp by doing our absolute value of the dot product of those two vectors. So all I need to do is just really get these into component form so that I can do that dot product. So 120 cosine 38, comma 120 sine 38 will be my vector P, and my vector R would be 1 cosine 25, 1 sine 25. And then it's calculator time. So 120 cosine 38 times cosine 25 plus 120 sine 38 times sine 25. So I get 116.92, and that's my answer. Luke, is that okay?
Yeah. I was just confused how to set it up.
Yeah, so the nice part here is that the shortcut was available there, so it just really becomes doing the dot product, which is not too bad. Jillian, your hand was up earlier. Do you have?
Oh yeah, did you finish 67 actually? Okay.
Oh, okay. Well, this just becomes the 0.23. This becomes the slope -5/7. So you just do y equals mx plus b. So I have 3 is equal to -5/7 times 2 plus b. So that's going to be 21/7 plus 10/7, so 31/7 is b. So I think that, assuming that my mental math didn't fail me there. But you just pull the point and the slope from the vector line equation and then just grind through an algebra 1 problem. Enzo? Sure. 12 asks us to find the component form for the vectors indicated below and then round your answer, yada, yada, yada. So we're told the magnitude of V is 2√2, and the direction for angle V is 5π/12. Notice here that the angle measure we're given is in radians. So either I should convert that to degrees or I need to make sure I use radian mode on my calculator. Either one is fine. I'm probably just going to change my calculator to radian mode, but either way of doing it is okay. So I'm just going to do magnitude times direction our magnitude times sine a direction, and then magnitude times cosine a direction. But before I go and start typing that into my calculator, I'm going to change to radian mode since I didn't change my answer or my angle measure. You know what I mean? If you had changed it to degrees, that would be okay to just leave your calculator in degree mode. I'm just going to have to remember to, as soon as this problem's done, to change it back into degree mode before I Mr. Kulik the next question and get the wrong answer because I forgot I changed my calculator's mode. So I have 0.73 and then 2.73. Does that feel okay, Jens? And I just changed my calculator mode back so I didn't forget. Good on me, Mr. Kulik. Alyssa?
For 71, I can find slopes and the points I can't seem to find. I kind of go for all the problems.
Okay, so keep in mind that there's infinitely many possible vector line equations. So if your vector line equation doesn't match the one in the back of the book, it might still be a correct answer, depending on which points you used. So like, for example, the point vector you could use would be, for 71, you could use -2,9. You could use 7,2. Or you could use some other point that lies on the line that connects those ones. Like, there's infinitely many points there to choose from. And then similarly, the slope for that would be what? Like 7/9 or something, right? Or you could write as -7 over -9. Or you could write as like 14 over 18. Or, you know, like there's infinitely many ways to write that slope. So there's infinitely many slope vectors. So you might still have the correct answer even if it doesn't match the answer in the book. There's like infinitely many forms for that.
Yeah. And then when you get like, so I know like the slope is -7.
Mm-hmm.
When you do it in the other form, which is like the R and V vector, do you do it like 0 over 7/9, or do you just like flip the 9?
Okay. So let's just run through this a little bit then. And just be specific. So you got the slope was -7/9, right?
Mm-hmm.
So that would tell me my direction vector V is 9, -7. Because remember that this is change in Y and that's change in X. So really the top part is the Y component, the bottom part is the X component. So if we wrote our vector line equation, I mean, I would just do that and be done with it.
Oh, you can just put like
Because this is a point,
yeah.
so that can be a point vector.
Okay.
There's my slope, so this is my direction vector. That's all I need to do.
Thank you.
Yep. And now you could use 7/2 or 7/2 as the point vector. That's fine. Or you could have done like, you know, -9 over +7 as your direction vector. That's fine. You know, like like there's like lots of different choices as to like how you kind of combine that stuff together. But any one of those would be fine. So there's like 4 different versions just using the information that's available there. Yeah, no problem. Not counting like if you did something weird and still could get a right answer by like choosing a point that wasn't given to you or turning that slope into something like that's not reduced. Emily?
So on I got like I think 35.01 or something. Is that like
It's probably the answer and the key used all the decimals on the calculator. Probably when you turned like when you found the hill vector or something, you probably rounded it to 2 decimal places and used those numbers. It's probably all it is.
okay.
As long as it's like clear and from your work how you ended up with the number, I'm not going to be like bonkers about the rounding if like the work is correct and maybe you rounded it more than I did. You know what I mean? But in general, when you see me doing the stuff on the calculator, I never round anything. I just pull the answer from the previous answer from the calculator to take all the decimal places or use the ANS command or whatever. And in general, like best practice is to like, ideally you'd like to do this all in one line. So there's the only rounding occurs is like on your final answer and not like on all the intermediate steps in between. But like, I'm not going to go like X out crazy unless it's not obvious what you did to like end up being a little off. You know what I mean?
Yeah.
Like if you have written down like what you're typing in your calculator on these steps and it's like, oh, okay, and you end up a little bit off from what I have, that's probably fine. Unless, of course, you did something silly and like it was supposed to be like 5.78, you wrote 5.87 or something down on your paper where it's like, oh, that's why you're off, is because you transposed 2 numbers or something. But that's all. Does that feel okay?
Yeah.
Yeah. And again, I know that this is difficult, and the last thing I want to make it is like extra hard because I'm worried like being super strict about the rounding or whatever. As long as you're communicating well what it is that you're doing and how you're getting your numbers, if there's a little bit of rounding because you rounded a bunch of intermediate steps, that's not the end of the world to me. Okay. Cool. And these are all totally fair questions. Like, like if I'm going to be assessed super hard on how I'm doing my rounding, I want to know so I can get practicing on that and figure out how I'm going to type this in my calculator so I'm getting answers that match. And preferably we'd like to do that, but I think this is hard enough right now without having to worry about like that extra piece of getting it in your calculator, the way Mr. Kulik would want you to, versus just like, hey, I did the right work. I just, goobered the calculator a little bit. You know what I'm saying? Anybody else? Jillian. 22. Okay. So it says to find the unit vector in the same direction and then write your answer as a component form and in linear combination form. So my equation to find a unit vector in the same direction is just 1 over the magnitude of your vector times the vector. So 6 squared is 36, 11 squared is 121, so that's 157. And then when I do the scalar multiplication and rationalize my denominator, since this is going to be my final answer, I'd prefer, not to have a radical in the denominator. So that's like my component form answer. And to turn this into a linear combination form, the linear combination form is the stuff with the i's and j's in it. But going back and forth between linear combination form and component form is kind of trivial. It just, the x component is the coefficient on your j vector, or your I vector, and your y component is the coefficient on your j vector. That's it. It's a So what I would say in general, if the radical in the denominator is a number, then yes. If it's like a variable expression, I would say that's probably not as necessary.
Okay.
But on problems like this, yeah, that's kind of the standard. And on any kind of multiple choice test, like an ACT or whatever, they wouldn't have radicals left in the denominator on their choices. So it's just kind of a good habit to get into. You get deep enough into mathematics, though, and nobody cares a hill of beans about radicals in their denominators. Like, the stuff is hard enough. Like, I'm not making this number look worse by doing this. It's just like, it's fine the way it is. But for right now, for whatever reason, we've decided to care as a mathematics community. I don't know. Eventually we stop caring. But I'm just trying to give you the honest answer. Like, you take Calc 3 and nobody cares. You know, like, this is hard enough. That's probably about where that stops becoming a thing. At least from a computational standpoint. Anyways, others, continue. These I'm going off on tangents, but it's okay, right? It's interesting tangents sometimes, if you're a nerd, which, I mean, hello. Anybody else? Jillian.
27. That's all I brought.
Okay. So 27 is the proof here, and this is the longest one, because there's really like 3 things to prove. I'm just gonna do one of the 2, and I think from that it'll be pretty obvious what to do with the other pieces, because it's like the same steps over and over again. So this is what we're trying to prove. Remember, C is a constant. I guess I should probably say that. So the first step is I'm just going to rewrite everything in component form. And then I'm going to follow the order of operations and do the stuff in the parentheses first. So I'm going to go ahead and do that scalar multiplication, C times U. And then I'm going to do my dot product. So far, so good. And now C times U C times U1 times V1. Those are just the product of 3 real numbers. So I know if I multiply 3 real numbers, the order in which I do that doesn't matter. So maybe let's say I'm going to multiply the C and the V1 together first, and then multiply the U. And I'll do the same thing on the other spot. Okay with that? This now is just the definition of a dot product. So that dot product must have been U1, U2 dot CV1 CV2. Okay with that? And then I can use my definition of scalar multiplication to just kind of go in reverse. Oops. Yeah, those are V's. To do that, which is exactly that. And it's the same thing for it's the same idea to do the other half. You're just kind of pushing the symbols around kind of in the same way. You just use your definition and I think at this step, you factor the C off and then use the dot product of the stuff on the inside, and then everything is fine. Right? You factor the C off, and then the inside is the dot product of U and V. So you have C times the dot product, which is, I think, what the last step is, or the last piece is supposed to say. Is that okay that I stopped there and just kind of talked about the other half?
Yeah.
And just like it's just a lot of writing that I just, it's like you did that half, like you get the idea. Not that I want to hand wave it, like proof is important, but I'm also trying to do a bunch of things today, so I don't want to like chew up 10 minutes, like doing something again that's like the same ish as the previous one. Okay. So I have a question for you guys. We can do the next section now, and when we finish, whatever time is remaining can be homework quiz time. Or we can do a timed piece of the homework quiz, because I still want to be able to do the next section at the end. Which one sounds better to you guys? I think it's to your advantage to do the stuff now, and whatever's left becomes the homework quiz. I think you'll end up with more time going that order. If that's okay to you guys. Okay. I just wanted to present you with a little bit of a choice. If anybody was like, no, I definitely don't want to do it that way, I would have been like, okay, that's fine. Okay, so section 8.5 is about the three-dimensional coordinate system. So when we draw our three-dimensional axis, we're going to kind of draw it in this fashion. So the dashed line, you have to imagine, is like coming out of the screen and going like back into the wall. Can you kind of imagine that? The way I like to think about it is I just take my finger and like kind of do this, where I have like my thumb is one axis coming out at me, then I have like my axis going to the left and right, and then I have the axis going up and down. You know what I mean? Maybe not, but like your thumb is the axis, one axis, one axis, one axis. So like the one coming into you, the one going straight up and down, the one going out. So the way we name these is going to bug everybody to no end. This one we call X, this one we call Y, this one we call Z. And you're like, what in the heck, Mr. Cool? Like, why did we do it that way? Well, we wanted, whoever did this first wanted the XY plane to be like, you know, this flat sheet. And then the Z is coming like straight up off the top of it. I don't know. Oops. Actually, we'll do it that way. There we go. I don't know why, but that's kind of the way they envisioned it. So the naming convention is stuck. So if I wanted to say plot a point, say I want to plot the point 3, 2, 5. So the positive part of the x-axis is the part that's coming out of the screen at you. So it's this piece. So like 3 on that. And the positive part of the y is the part on the right, as you'd expect. So there's 2 units there. And the positive part of the z is the straight up and down, or the up part. So 5 units there. Everybody's okay with that idea? Yes, Jillian?
So the positive direction is the one toward us?
Yes, on the x-axis. Yep. So this is like the positive end. That's like the negative end. That's the positive end of the y, the negative end of the y, positive end of the z, and the negative end of the z. Okay. So, little bit tricky now. How do I plot this point in 3 space? Well, what essentially we're going to end up doing is drawing like a box. So I'm going to start by kind of drawing the bottom of the box. So the bottom of the box is going to be in the xy plane. So I'm going to draw here a side that's parallel to the x-axis and a side that's parallel to the y-axis. And that corner then there, I'll use a different color. I didn't do a very good job. Let's try that again. That looks a heck of a lot more parallel. So that corner then has x value of 3 and y value of 2. Everybody okay with that? Okay. Now what I'm going to do is I'm going to translate, I'm going to draw a side of the box. So one side is here, and another side is here. Everybody's okay with that? And then I'm going to draw another side that's like the same length, but is coming from here. I'm just eyeballing that a little bit. Everybody okay? And now I'm going to finish drawing the rest of my box. And it's this point then here that is 3, 2, 5. So basically what we drew down here in red was 3, 2, 0. And what we did is we made sure that that piece was 5 units up. Which means that the thing in green that we drew there is like 3, 2, 5. Okay with that idea, Katie?
So do you write it in order?
Absolutely. Yeah, when we plot points, they're in alphabetical order. Sure. Absolutely. Yes. So really what we did here in more mathematical language is we took this point in 2-dimensional space in xy, and then we projected it up into 3-dimensional space. So instead of it being at the z-coordinate 0, the xy plane, we projected it up to the z-coordinate 5, having the same xy plane, so we're just kind of like translating that point, or that entire plane up. Does that, you kind of see that? Now, what if we wanted, so that's how we can plot a point in 3 space. What if we wanted to point or draw a vector in 3 space? So notice that this is a component form vector. You can tell because it has wedge brackets instead of parentheses. Do I need to draw those sharper? That's pretty sharp. They're okay. So we're going to start the same way. Remember when we graphed a vector in 2 dimensions in component form, we just plot the point and draw a line from the origin to that point, right? So it's going to be the same idea here. So we're going to plot the point in 3 space, in 3 dimensions, and then draw our line from the origin, the point 0, 0, 0, to the point we've graphed. Okay? So we'll start here. So again, we have 2 units in the x direction, 3 units in the negative y direction, and then 4 units in the z direction. So I'm going to start by drawing like the bottom of my box. So this is the point like 2, negative 3, 0. Everybody's cool? Okay. And then we'll draw the rest of our box. So we're drawing up, up. So we're drawing that first face of our box. And then we'll do the same thing here. So I want to draw this about the same length. So this then is our point 2, negative 3, 4. Everybody feel okay? And then to draw our vector then, we start at the origin and we draw to our point. So our vector is the piece in green there. I know there's a lot of stuff going on. When you do this yourself, feel free to use multiple colors if it helps. Make it more clear when you go back and look at it. Or if you want to erase your box once you've got your point in the right place, or use the dashed lines to do your box or whatever, like any of that kind of thing that helps make this a little bit more readable is totally fine. Because again, it can get a lot going on, right? Everybody feel okay though? Jillian? So that's just it's just a vector. It's component form vector, right? Because it's got the wedge brackets. We call that component form. So 2 things worth talking about real quick. What does the distance formula in 3 dimensions look like? Well, remember in 2 dimensions, it's x1 minus x2 squared plus y1 minus y2 squared. Everybody agree with that? That's 2D. Into 3D, we just have another one for the z component. Okay, Mr. Kulik. That's exactly what I was hoping it was going to be. It's basically the same distance formula as before. We just add another thing in there, like a big stinking whoop. I can handle that. I might even remember that because it's like I just keep doing what I was doing, right? Doesn't matter how many components I have. If it was 4 dimensions, you just keep going. You know what I mean? Very easy. I guess 4 dimensions distance doesn't really have much of an analog there. I don't know what that would mean. So the midpoint formula in 3 dimensions So in 2D, it would be x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. And then in 3 dimensions, maybe I'll do that. z1 plus z2 divided by 2, because we need a third component. Again, super happy with that, right? Like, it's exactly like 2 dimensions. It just, you keep on going and following the pattern. Does that feel nice and easy? Should. We'll do a little bit of 8-6 now, and then we'll stop, I don't know, in 10 minutes or so. That gives us like 25 minutes to do the homework quiz. That should be more than enough time, ideally. So 8-6 is just kind of going back and reviewing all our 2-dimensional definitions and just kind of updating them for 3 dimensions. So our component form is just, instead of the component AB, it's the component ABC. What did he do? IB component form. Well, instead of being the column vector AB, it's the column vector ABC. The linear combination form, instead of being A times the vector I plus B times the vector J, we also now have plus C times the vector K, where I is the X component, J is the Y component, and K is the Z component. And these were the, these were called some kind of unit vectors, right? Or the standard unit vectors, that's what these things were called. Everybody's cool? So again, like nothing really different than 2 dimensions. It's just like, yeah, okay, there's a 3rd dimension. I got a 3rd little piece to this, big whoop. So like magnitude, so if I have, you know, a component form vector, ABC, it just becomes a squared plus b squared plus c squared square rooted. Exactly like the previous one was, we just have another component, right? I mean, the head minus tail rule works the same. So if I have x1, y1, z1 as a point, and x2, y2, z2 as another point, say, I guess we'll call those A and B. The vector AB is then head minus tail, head minus tail, head minus tail. The exact same, you know, like the same idea as in 2 dimensions, right? Just have a 3rd component. Keep in mind, in 2 dimensions, we describe the direction of a vector with an angle measure, right? Does that make sense in 3 dimensions? No, right? An angle only makes sense in like a plane, not in a 3-dimensional like sphere. So we're going to end up using we'll be using like direction vectors in 3-dimension rather than a direction. We'll get to more to that later. But there's no real, when we talk about direction in 3 dimensions, it's not an angle. So like our vector operations, you know, if I have 2 vectors, and I wanted to add them together, well, the addition works the same way. Feel okay with that? Subtraction works the same way. I guess we'll do scalar multiplication works the same way. Dot product works the same way. Everybody still feeling good? And all of our dot product properties from 2 dimensions hold. So nothing changed there. Well, that's pretty cool, Mr. Gulick. That's it's no big deal. So for example, if I wanted to do, if I know U is -247 and V is 7I minus 6J minus 9K, and I wanted to do 2U plus V, well, that's going to be 2 times U, so -4, 8, 14, and then V is just going to be 7, -6, 9. When we add those together, I got 3, 2, 23. Oh, that should be -9. 5. And then we could, if you wanted to, if the directions asked, you could graph something like that, just like we did previously. But nothing different, right, with 3 dimensions. All of the things we've looked at here, other than direction, exactly the same. Nothing got harder. Everything just got a little longer because there's a 3rd component to worry about, but it's all working exactly the same. We're going to stop here for today. At this point, you guys could be able to do now, so look here, number 77 through, do that, 94. When's that, what problem set is that going into? Yeah. And we'll,
Did you make this a hybrid quiz?
no.
It should be okay, dude.
It's not.
Yeah, but Yeah, try.
And you guys will need the projection formula for the last problem. So take a moment and just kind of write this down somewhere, because I'm going to kill the projector here in a minute while I go and do some other stuff while you guys are working on this. But for that last problem, you need the formula for the projection of a vector. So I forgot to type it in there, so I'm just going to give it to you right now. All right, this is the projection of V onto U is equal to the dot product of U and V divided by the magnitude of U squared times the vector U. Anybody still working on copying that down? Is that, Alyssa, are you writing it?
Yeah.
Okay. That's okay. You should just be like, yeah, give me 1 second. That's totally fine. I just wanted to, okay, cool. And Maddie, we're done doing stuff for today. Everyone's just working on the homework quiz from here on out. So I'm going to kill the Zoom feed.